beginning, when space and time started in the hot fireball we call the Big Bang, the whole universe could be described by just one all-embracing law. But as time passed, the universe cooled. Simplicity became complexity, and the familiar world developed of change and diversity. Today, the simplicity has vanished, but it may be that it could be recaptured if the fundamental laws of matter could be worked out. Then the ultimate goal of all physics would be achieved, the goal which science has searched for throughout its history, the discovery of a single complete theory to explain all physical phenomena, life, the universe, and everything. A new generation of physicists now thinks it may be close to recapturing that original simplicity, finding the lost equation which would tie all physics together.
And then the fact that this is equal to plus this, I choose to be a boson. And the fact that this is equal to minus this, I choose to be a fermion. This is a boson and this is a fermion.
So I think what happens here is that you have people who really feel that they are learning something about the universe here. People are excited. They feel that new physics is opening up. People want to leave their mark in physics, and they feel that, in fact, there is a chance here that this is important. I think it's an enormously healthy time in physics. The controversies are very, very productive, and eventually this may work out, and we will find out what the real theory of the universe is.
But there's a problem. As theories have become more daring, encompassing more fundamental ideas, experimental tests have become more remote. A new and daunting thought has in recent years started to take root. Science may now be facing a dilemma that it has never had to confront before. That as physicists finally approach the ultimate theory, so they may be obliged to lose contact with experiment or any means of testing whether the theory is right. And as they get nearer to their ultimate goal, must they at the final hurdle desert the cultural heritage of science itself and find themselves in a world of belief based only on faith and aesthetics? If ever a scientist believed in the power of aesthetics to produce truth, it was Albert Einstein. He's justly famous for producing the theory of gravity which is still believed in today, but the greater part of his working life was spent trying to extend his ideas into a complete description of all phenomena. In 1928, the equations of Einstein's latest theory were even posted in the windows of Selfridges, the famous London store. A friend wrote that crowds had stopped to look at them. But Selfridges had been overconfident. Einstein's equations never quite worked out, and the most famous scientist in history died knowing that his life's goal was unrealized.
I myself don't believe that there can be a complete theory of everything. On the other hand, we have today what you could regard, or what the layman could regard, as a complete theory of everything. That is to say, we know why copper is red and why the sky is blue and what rainbows are, how people are born and how they grow and how plants grow. These things we more or less know. We have a theory. It is, in a sense, complete. But we can always search for further mysteries. If we understand the things we see, we buy a microscope, see smaller things. If we still understand everything we see, we build an accelerator, which can look at smaller and smaller objects. As we build larger telescopes and larger accelerators, we will, I believe, forever discover new mysteries, which will require new science. And I don't think we will ever get to the root of things, at least not for the next million years of a healthy human culture.
But since Einstein, that search for a single fundamental theory has continued. It's a story that takes us to the limit of experiment, deep underground where giant tanks of water lie in wait for strange particles. out into observations of the wider universe in pursuit of missing neutrinos created by the Big Bang, and down into the innermost parts of the atom, where particle accelerators collide matter and antimatter in tiny recreations of the start of the universe. Science has known for 100 years that all the objects in the world are made of the same sort of particles. A tree is a complex arrangement of atoms and molecules, but all the constituent parts are known. Scaled down some 1,000 times, we see the individual cells and fibers. Smaller as much again are individual molecules. Each atom reveals layers of electrons around a nucleus of tightly packed protons and neutrons. And at the smallest level known are the quarks, which make up each proton or neutron, and the individual electrons which orbit the nucleus. We can also look outwards to the furthest reaches of the universe. 1 million trees would barely span our own Earth. The Earth and solar system itself are but tiny specks within a complete galaxy. And galaxies in their turn are mere dots in the full span of the universe. It's in the early moments of the Big Bang that the very large and the very small come together to give us a unique insight into the fundamental particles of matter. But at the moment, the most important characters in the story are not the particles themselves, but the forces which make them move. There are 4 of them. Everything in the universe depends ultimately on these 4 forces. Each one plays a specific role. Gravity shapes the universe. It keeps the planets in their orbits and holds the galaxies together. Electromagnetism is responsible for light and radio waves. It holds atoms together to make solids and liquids. The weak force is involved in radioactivity. It is what makes the stars burn. The strong force holds the atomic nucleus together. It makes atoms possible. To achieve the goal of an ultimate theory, science must show that these 4 very different forces are related. That in the distant fireball of the Big Bang, they were all unified into one primal force. It is believed that as energy and temperature are increased, beyond even the levels inside the stars, the forces come together and bit by bit, the lost unity is uncovered. No experiment will ever be able to journey to the far regions of unification. The energies required are just too high. But a theory has already taken the first momentous step. A connection has been made between 2 of the forces, the electromagnetic and the weak force. An extra monument has been added to the landscape. This newly combined electro-weak force predicted 2 new particles. Their existence has only just been confirmed by experiment. In the Geneva countryside at the European Laboratory for Particle Physics, called CERN, protons and antiprotons were made to collide at enormous speed. Strange particle tracks were produced, whose secrets were probed in one of the most spectacular scientific experiments of a generation. The tracks confirmed the unity between the 2 forces by revealing the 2 new particles called the W and the Z, which had never been seen before. The experiment not only showed that the particles existed, they had exactly the masses predicted by the electro-weak theory. In 1984, the Nobel Prize for Physics was awarded to Carlo Rubbia, the leader of the team. Science had followed its classic pattern, a theory later confirmed by experiment. What the CERN team had done was to push technology to its limit and increase the energy of the collisions far enough to make the 2 forces remember their common ancestry for just an instant. The next step is to go beyond 2-fold unification and develop a theory which predicts that at higher energies there is an even more distant monument, one which brings the strong force into the scheme and unites the weak, electromagnetic and strong forces in a threefold unification. The theoretical tool which can unravel the links between forces and predict a new particle is the idea of symmetry. Symmetry is a familiar idea from everyday life. We see it in nature and in art. But in science it has a slightly wider meaning. To understand it, it's best to forget preconceptions and find a new definition. A checkerboard remains a checkerboard even when the black and white squares are swapped over. This is the way to imagine symmetry in science, something remaining the same when two things are swapped over. This ties in with the original idea of symmetry. The symmetric ice crystal can be rotated, and although the frame has moved, the drawing remains in the same place. Just like the checkerboard, two things can be swapped over, leaving the drawing the same. This simple idea has far-reaching results. To understand the whole universe, there must be laws which are true everywhere, on the moon and on the Earth. That's a constraint on all theories. They must be symmetric between any two places. Symmetry can be a problem, too. In the story of Buridan's ass, the donkey is in a symmetric position. It starves because it can't decide which carrot to eat. In the donkey's mind, the left and the right-hand meal are interchangeable. Physicists find the symmetry which unites forces in equations. Newton's equation of gravity talks about force between two masses, m1 and m2. The formula is the same if m1 and m2 are swapped over. They could be the Earth and the Moon, for instance. They can change position in the equation and it remains the same. Newton's law obeys a symmetry between different objects. Einstein looked at the universe and imposed another symmetry. He made the laws of nature the same for an observer standing still as for somebody moving. This symmetry led to a revolution in thought, which produced the famous formula E equals mc squared, and a new way of looking at space and time. But Einstein went one step further. He demanded that the laws of nature be the same for an accelerating observer. General relativity, Einstein's theory of gravity, one of the greatest and most beautiful scientific theories of all time, which has led us towards an understanding of the universe, is the product of the simple idea of symmetry. The threefold link is a distant landmark. There is a consistent theory, but no accelerator team of the future will be able to confirm its existence in the way they have for twofold unification. What they can do is listen for echoes of that distant time among the familiar forces and particles of the world around us. There are some such echoes. Perhaps the most startling is this. If that distant unification is real, the basic building block of matter, the proton, should decay. This is because the different forces don't act on the same kinds of particle. The electromagnetic force acts on electron-like particles, but the strong force acts on the other species of particle, the quarks. If the two forces are linked by symmetry, then the particles they act on must be able to swap over while the unified force remains the same. So an electron must be able to turn into a quark, and vice versa. Once again, a belief about symmetry leads to a concrete prediction. A proton consists of 3 quarks. If one of them changed, the other 2 could not live without their partner, and the proton would explode. Everything is made of protons. The idea that all matter will eventually break up sounds alarming. But the process is so slow that in this tank of water, only 1 or 2 protons are expected to decay in a month. Experimenters are hoping that by waiting long enough, they'll be able to spot a proton breaking up sending tiny flashes of light through the tank. Banks of photo tubes around the walls would pick up the flashes. It's a long wait. In fact, a team from the University of Michigan, the University of California at Irvine, and the Brookhaven Laboratory has been standing by to observe a decay since the summer of 1982.
Okay, so we can then shut off.
The snag is that other particles may mimic the process, particularly cosmic rays. So the IMB team buried their experiment some 2,000 feet underground in the caves of a salt mine near Lake Erie. Several similar experiments have found homes in equally exotic surroundings. But even at these depths, some maverick particles still get through. At the University of Michigan, computers are busy trying to spot the rare patterns of light that would signal proton decay. A reconstruction of exactly when each phototube was hit reveals some quite distinctive features. But are they what's expected? Proton decay should be recognizable by characteristic back-to-back signals, the light from which will illuminate just a few of the phototubes in any cross-section of the tank. There are two types of cosmic ray particles which produce signals to confuse the experimenters. One of these is the muon, produced high in the atmosphere. Several of these penetrate the tank each day. It can be identified as complete walls of phototubes are lit up by a continuous swathe of light. The second offending particle, the neutrino, produces a more discrete signal, lighting only a few tubes. Since 1982, millions of events have been recorded. Most are unwanted background. But what of the remainder?
The experiment's gone extremely well. We have not found the expected events which were on the simplest version of grand unified theories. This is a little bit disappointing and somewhat embarrassing to the theoreticians, but I would say at this moment it doesn't rule them out, but it's a little bit embarrassing for them.
During 1984, the whole IMB experiment was redesigned. By autumn, the first new readings were in the can and on their way to the computer.
Well, we've just completed our first data run, and we're bringing the tapes back to the University of Michigan and sending some to the University of California at Irvine for the first pass analysis, where we'll be taking a look at this data for the first time with the upgraded detector. We record about 250,000 events per day. Most of these are through-going cosmic ray muons, which are not what we're looking for, of course. In our first 204 days of analyzed data, we had something like 169 neutrino interactions. Nine of these events were indistinguishable from being proton decay or a neutrino interaction. Now, we hope with our upgraded detector we'll have a better ability to distinguish actual proton decay, let's say, from a neutrino interaction that mimics proton decay.
This run is, if anything, more speculative than the earlier search. It could be a long haul. The theories of threefold unification make another bizarre prediction in a very different realm of physics.
When Maxwell made his theory that put together electricity and magnetism, he noticed something. He noticed that there could exist particles that have an electric charge that are the sources of electric fields. A few years after his theory, these particles were discovered. They are called electrons. There could also exist particles that are the sources of magnetic fields, from which magnetic fields come. He imagined that those particles also exist, but it seems they don't, or at least until the present day, nobody has ever found a particle from which magnetic field comes. If I may make a picture on this piece of cork, an electron, for example, E for electron, is a source of electric field. That means coming from it, there's an electric field that points out in all different directions. Now, a magnetic monopole is exactly the same thing. It's a fundamental particle which is the source of magnetic field lines. A magnetic monopole, a hypothetical particle, from which magnetic lines of force would come out in all directions. Now, the only kinds of magnetic systems we can make are things that look like this, magnets. Magnets are things that have a north pole and a south pole. They do produce a magnetic field, but the magnetic field comes from one side and goes to the other. It has lines of force that look like this. Now, what a magnetic monopole is a north pole without an associated south pole. So you might say, that's simple, just break the magnet in half and you have a north pole and a south pole. But it doesn't work like that, because a north pole is created here and a south pole is created here, and you end up with a smaller magnet. You can imagine doing this again and again, continually cutting a magnet into smaller pieces. You finally end up with a single atom, which is also a magnet, but it too has a north pole on one side and a south pole on the other. You can tear the atom apart. You end up with an electron. The electron is also a magnet, but it has both a north pole and a south pole.
In threefold unification theories, monopoles are predicted to be heavy particles. They've been looked for in accelerator experiments, but the energies available are far too small. You'd need an accelerator millions of miles across to find them.
There was an accelerator of just that kind once, and only once, in the history of the universe. The original Big Bang, the tremendous explosion from which our universe evolved and is still exploding, this explosion was of an immense energy, far beyond any energy we can produce or will produce in the laboratory. It was energetic enough to make magnetic monopoles, if there are such things.
As matter was thrust apart in the seconds after the Big Bang, the fabric of space and time evolved with it. Early on, odd contortions of space and time would have been present. It's in the folds of this space that monopoles may have been produced. But if such exotic particles do exist, where does one start to look for them? Do physicists have any guidelines?
Now, the logic that is employed in this search is that which the French call the logic of the lamppost, which goes as follows. Suppose you go back to your home at night, a little drunk and walking, and when you get to your doorstep, you find that you have lost your keys. Where are you going to go back and look for your keys? Well, you will look for your keys under the lamppost, because should they be in the dark, you wouldn't find them anyway.
The best lamp for spotting monopoles is thought to be deep underground in exactly the same places used for proton decay. Monopoles flying through an isolated chunk of matter are expected to trigger or catalyze the disintegration of a number of protons.
Imagine a monopole moving through the detector, catalyzes one nucleon decay, catalyzes another nucleon decay, and so on. So we would see a sequence of nucleon decays separated by a short time interval. And that's a very characteristic signal. We look for that. We haven't found any evidence for it.
This reverse is not necessarily the end of the search for monopoles. The lack of monopoles could be explained by a new model of the Big Bang in which the universe did not expand uniformly, but underwent a sudden expansion or inflation. This expansion would have caused space to evolve with fewer folds in it, so very few monopoles would have been produced. Nearer home, the fate of another particle also depends on the theory of threefold unification. Produced by nuclear reactions in the sun, the neutrino was originally thought to have no mass, like a photon of light. But the new theories suggest the neutrino may have a small mass after all, so scientists are now going to great lengths to measure it, even right under the core of a pressurized water reactor. Neutrinos are produced in abundance by these reactors, which provide a more controlled source than the sun. Perhaps the most accomplished measurement of the neutrino mass comes from a Russian experiment at the Moscow Institute for Theoretical and Experimental Physics. In 1984, they concluded that the neutrino seems indeed to have a mass 1/17,000th that of the electron. But even this respected experiment takes measurement once again to the limit of what it's possible to discern. Some say beyond. The results of all the experiments on threefold unification are so far inconclusive. It seems to a growing number of physicists that they should reject the constraints of the experimental lamplight, which only allows them to look in certain places. They believe the time is ripe for them to achieve what Einstein never could, a theory of fourfold unification of all four forces, including gravity. To do this, they have to imagine energies beyond even the still unconfirmed point of threefold unification, because only there is it even remotely possible that gravity will show any unity with the other forces. To go this far is not only to go way beyond experimental testing, but also to encounter immense difficulties in the theory. After all, the attempt to include gravity defeated even Einstein. But that story may have an ironic twist. In 1919, the very year that Einstein achieved world fame, Theodor Kaluza, a young German physicist, made a remarkable discovery. He took Einstein's equations of gravity and wrote them down as if they applied to a different world, not the four-dimensional world of Einstein, but a mathematical universe with an extra fifth dimension.
To his amazement, he discovered that he had actually, when rubbing off the fifth dimension, the fifth coordinate, explicitly from the equations, he found that he had written down not only the theory of Einstein's gravity in four dimensions, the normal gravity, but also Maxwell's electromagnetism on the right-hand side of the equations. And so this was the first unification of Maxwell's electromagnetism with Einstein's gravity, achieved by extending space and time to 5 dimensions rather than 4. An incredible and a miraculous idea.
In mathematics, an extra dimension is a matter of algebra. One dimension, a line, is represented by one number, x. A two-dimensional surface by 2 numbers. Ordinary three-dimensional space by 3 numbers. You can't draw another dimension because there's no room for an extra line, but we can add an extra letter. In fact, mathematics can be done in any number of dimensions. Human brains are not wired in the right way to imagine life with an extra dimension. We're in the same position as a two-dimensional flatlander. In his world, he cannot imagine our space. If we push a pencil through his plane, he can't know where it's come from. All he sees is a circle which grows out of nothing for no apparent reason. Only flatland mathematicians can imagine the pencil which caused the phenomenon. We can perform tricks for the flatlander. To him, this disk is permanently stuck inside the ring, but with an extra dimension it can be picked up and moved, leaving the flatlander mystified. Kaluza had performed just as amazing a trick in physics by adding an extra dimension. It was quite obvious who should be told about his discovery.
What Kaluza did was he sent the paper to Einstein and asked him to get it published. And Einstein's reaction to this idea is in his letter. The idea that this can be achieved, that is to say the unification of electromagnetism and gravity can be achieved through a 5-dimensional world, has never occurred to me and would seem to be altogether new. I like your idea at first sight very much. This was in April 1919. Then a week later, he writes again, raising a few, what now appear to us, rather trivial points or difficulties.
There was always this Einstein asked a question or made a suggestion, and then my father did something about it, sent it to Einstein. Einstein repeated or asked another question, and so on. There are 5 or 6 letters of this sort.
And then suddenly, in October 1921, 2.5 years later, he writes himself to Kaluza saying, I am now having second thoughts about having restrained you from publishing your idea on a unification of gravitation and electricity 2 years ago. I wish I shall present your paper, if you wish, I shall present your paper to the Academy after all. And then he did.
About 22, he went to a congress of physicists, and there was much interest. At least my mother told us children that after his lecture, there was a discussion of almost an hour. but later on I never heard again of these things.
So it's a very curious story that the idea which we are today finding to be the most promising in terms of getting a theory of unification of gravity, electromagnetism, and nuclear forces by not concentrating on 5 but on many dimensions was something which Einstein completely neglected throughout his life. It's a curious, unexplained fact.
Kaluza's idea was picked up and improved by Oskar Klein in Sweden, but both men lived to see it become little more than a historical curiosity. Kaluza's disappointment must have been enormous. At the moment when he saw how to combine the two great forces, it must have seemed to him that it couldn't be an accident, that some profound secret must have been revealed. His son was a small boy of 9 at the time, and he used to sit in his father's study when he was working. Usually, the father would work quietly by himself.
But one day it was quite different. He sat completely still for several seconds, and then he whistled very sharply and banged the table, and he stood up, and but he remained completely motionless for several seconds, and then he began to hum an area, or the last part of an aria of Figaro. Dum dum da dum dum da 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 dum dum diddly dum da 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 da.
Kaluza-Klein theories have been resurrected in a 10 or 11-dimensional form in connection with a new kind of symmetry, which goes under the grandiose title of supersymmetry. There is hot debate as to whether supersymmetry is the correct road for theoretical physics to follow, but at the moment, supersymmetry is by far the boldest attempt to produce a single theory of all forces and matter in the world. A symmetry in theoretical physics can be used to link things together. Supersymmetry takes the audacious step of linking two apparently fundamentally different things. It links particles with forces. The idea isn't so crazy as it sounds at first. At the very small level, every force is carried by a particle. Each force has a particle inside it. Gravity has a graviton. Electromagnetism has a photon. The weak force has the W and the Z. And the strong force has a gluon, so called because it glues quarks together. Supersymmetry joins the force carriers with the particles of matter with a symmetric link. If this connection is valid, it'll be one of the most impressive steps yet taken towards a complete unified theory. One of its payoffs is that it opens the door to the inclusion of gravity with the other forces.
In fact, supersymmetry goes even better than that, because not only is it compatible with the unification of gravity, you can actually show that supersymmetry implies gravity. And in fact, if we didn't already know about Einstein's general theory of relativity, supersymmetry would force us to invent it.
Supersymmetry implies gravity because the symmetry isn't quite perfect. As a particle is transformed into a force carrier and back, it moves slightly, and this movement is compensated for by the addition of a gravity-like force, supergravity. The followers of supergravity and supersymmetry met in Bonn in 1984. This is the point where the search for a fundamental theory turns in on itself. These physicists have cut themselves off from the world of experiment. The theories they contemplate are not believed because of evidence, there isn't any, but because of their internal qualities. The ideas in the new theories seem to fit together elegantly, like the pieces of a puzzle. One of the pieces is the multidimensional idea of Kaluza and Klein. To achieve supersymmetry in its most powerful form and include gravity, today's physicists found that, like their predecessors, they had to imagine a world with extra dimensions. It's an extraordinary idea, but there are some theorists who believe we're living in a 10 or 11-dimensional world. The reason we don't notice the extra dimensions, they claim, is that they're curled up very small, so their effects are only felt indirectly. The universe may have started with 10 or 11 dimensions, but at some stage they collapsed, leaving the 3 dimensions of space and 1 of time that we see today. If these ideas are right, then the history of the universe begins with just one thing: a multidimensional field which is the ancestor of all today's particles and forces. Quickly, the cooling universe loses its extra dimensions. The single force splits into 4, and in 10,000 million years, we observe the result. There's one extra thing that physicists hope for in a fundamental description of the universe: that it should uniquely define just one kind of world. This would mean that if science was in possession of the true fundamental theory, you could ask whether the laws of physics could have made electrons the size of footballs, or the sky green and trees blue. And the answer would be no, these things are not possible. The fundamental theory says that there is only one way for things to be. Some of the new theories seem to have that property of uniqueness. They achieve it because the constraints of symmetry narrow down the choices open to theorists.
Well, physicists have very fertile imaginations, and so there are lots of different theories they could think of which might correspond to the real world. And so to narrow down the choice, we like to invoke this idea of symmetry in the hope that we can eventually pin down the correct theory. And as a crude analogy, let's imagine that each one of these shapes represents a possible theory of elementary particles. Now you'll notice that we've been careful to choose shapes that have the property that if you flip them around their vertical axis, you get back to where you started from. So in the spirit of this analogy, let's suppose that this represents the symmetry of the electroweak forces. We're fairly confident that the electroweak theory is a good theory, so we're not interested in theories that don't have that symmetry. But we want to go a step further. We also want to incorporate the symmetry of the strong interactions. So by analogy, let's suppose that this corresponds to flipping around a horizontal axis. Now we see that some of the shapes remain the same, whereas other shapes do not. In other words, some theories have the symmetry of the strong interactions, other theories don't, and so let's eliminate all those theories that don't have the symmetry of the strong interactions. Well, we've managed to narrow down the choices a little, but we've still a long way to go. However, at this stage, it's no longer clear what the next symmetry should be. Suppose we say, for the sake of argument, that it's supersymmetry. Let's represent supersymmetry by rotation about a diagonal axis. Once again, some of the shapes remain the same, others do not. And so we can eliminate all those theories that don't obey the principle of supersymmetry. If, on the other hand, we demand maximal supersymmetry, that's to say the most supersymmetry that the mathematics will allow, which we can represent by rotation about every conceivable axis, then we rule out all but one unique theory. The question, of course, is, have we painted ourselves into a corner? Is this one unique theory actually describing the world in which we live?
All the proposed new theories are complicated. To believe in them, you have to be persuaded by their inner simplicity. not everybody is. Sheldon Glashow looks at these new developments with skepticism.
It's just some kind of abstract elegance. In fact, I'm thankful to supersymmetry because there are something like 1,000 high-energy theoretical physicists in the world. A large fraction of these people are working on supersymmetry. That keeps them out of my hair, leaves some room for me to do other things which have a better chance of working out. Many of my friends have been doing supersymmetry for the past 20 years. It's a vast endeavor, it's a fascinating theory, it's an ingenious theory. It has accomplished, in terms of explaining phenomena, absolutely nothing. It does predict the existence of new particles. In fact, as you know, there are 17 particles in our bestiary at present in the standard theory. It doubles them. It says there are precisely 34, maybe more, fundamental particles. It gives them nice names: winos and binos and photinos and gluinos, sleptons and squarks. The trouble is that not one of these new predicted particles have been found. I like new theories that predict new particles that are found in the laboratory. I do not like new theories that predict all sorts of things which are not found and perhaps cannot be found.
The prediction of extra particles is perhaps supersymmetry's weakest point. It happens because when supersymmetry turns a particle into a force carrier, the force carrier isn't one which is known to physics. A quark, for instance, is meant to have a superpartner called a squark, which as yet has never been detected. A lepton becomes a slepton. A photon, a photino, and, strangest of all, the W and Z become the wino and the zeno. Supersymmetry's critics feel this is ridiculous.
On reflection, I don't think this is really a fair criticism, because what really matters is not how the theory looks at the comparatively low energies that we study today. Low, that is, compared with the typical energy of the gravitational interaction. What really matters is whether the underlying fundamental theory, which we don't see in its pristine form at these comparatively low energies, whether that underlying theory is beautiful and simple. And when you come to supersymmetry and supergravity theories, even though the theory you end up with at low energies appears to be rather clumsy, with doubling and so on, the actual underlying theory is the epitome of simplicity and elegance.
Simplicity and elegance are allied to beauty in physics. Keats' famous line, "Beauty is truth, truth beauty," is remarkably far-reaching. It doesn't just say that the truth is beautiful, it says they're the same thing. If you have beauty, then you must have truth and vice versa. This is what supersymmetrists have to believe, that their theories are guaranteed truth by their own elegance. Einstein plainly felt that this had happened with his theory of gravitation. He declared it too beautiful to be false. The problem is that it only takes one contradictory experiment to disprove a theory, and when the stage is reached that no more experiments are possible, scientists will always be left wondering whether their ideas were beautiful enough. That's Abdus Salam's warning about multidimensional theories.
I must confess that one cannot say that the aesthetics of man are the same as the aesthetics of the Lord. They may be very, very different. I would not like to say that this is the final theory, but I would like it to be correct, if it's possible, to test it properly.
Kaluza himself was able to confirm a piece of theory in a very spectacular way. He taught himself to swim by reading a book. After a day's study, he felt confident enough about the theory of swimming to perform an experiment. He took the whole family to a nearby lake.
He really swam so that we could see it 50 meters in one direction and back. We children were impressed by an idea of these things, that if somebody said that this is theoretically right, it may be really right.
Kaluza's faith that a good theory will ultimately be borne out by experiment may turn out to have been justified by more than just a trip to a lake in Germany. The very experiment which confirmed the unification of the electromagnetic and weak force in 1983 is now producing data which don't fit in with any theory.
The latest news from CERN is extraordinarily exciting. Just this year, Carlo Rubbia has announced not only the discovery of the W and the Z, but subsequently anomalies, strange new effects.
The events in question are characterized by a strange imbalance in the particles produced, more off to one side than the other. That one-sidedness is just not possible in physics, so the implication is that something crucial is missing.
So far, there are about 5 very curious new types of phenomena that have been reported from CERN. Some of them are called Zen events. They're events where particles come streaming out in one direction, nothing comes out of the other side, the sound of one hand clapping. It's a strange business, and these curious anomalies simply don't fit in the standard theory. They're not part of it.
On the other hand, there is a truly remarkable possibility. Although the four-fold unification with gravity implied by supersymmetry would take place only at enormous energies near those in the Big Bang itself, physicists may have been lucky enough to have picked up a hint that they're on the right track. Excitement is mounting that buried within the debris that produced the W and Z may lie the first traces of one of the extra particles predicted by supersymmetry. Could this be the first evidence of a photino, or a slepton, or a squark? Or could it be something that'll force physicists to revise their ideas completely? It could be years before an answer is found, but whatever they are, these pictures are part of scientific history. Almost infinitely rare, almost impossible to create, they now represent a puzzle which science will want to solve.
People often come to me and they say, what is this that you're doing for? Why should the United States government spend millions and millions of dollars to build a new machine? Will it lead to a new kind of toothpaste or something like that? And I have to say to them that mostly the answer is no. What I usually say is this. I say that people differ from other animals in that they have curiosity. They look at the stars with wonder. We might try to teach dolphins and chimpanzees to speak, and sometimes we're successful, but they're sure not going to look at the sky and imagine constellations. This is the way in which people, or at least little children, differ from animals. Little children are curious. My kids ask me, where does the sun go at night? And how come I can suck a soda up through a straw? And questions like this. Later in life, they are trained not to ask questions of this kind. They go off to school, they become doctors and sweepers and lawyers, sellers, marketers of useless devices, things like this. Not all of them. Some of them maintain this primordial human quality of curiosity. Some of these people become artists, like the man who made that. Some become composers, some become physicists, some become astronomers. These people, in a sense, have kept the faith. They really want to know what's going on.
It's hard to imagine that there will not always be people who want to know what's going on. Their quest will only be over if a time comes when there are no more puzzles to solve, when most physicists are agreed on what the world is like, and further investigation is impossible anyway. Then humanity will have come as close as it ever will to a complete understanding of the universe.